All right, so for Algebra 2 today, we are shifting to section 2.6. We're going to start talking about families of functions and transformations of them. Your goal when you leave this class at the end of the year is to be able to tell me the shape of different functions. If I asked you, what does a y equals x squared graph look like? You would say what? Y equals x squared. What is that shape? A parabola. Yeah. All right. If I said y equals 2x minus 3, what is that? 2x minus 3. A line. Yeah. So if I give you an equation, you should be able to tell me the general shape of it. All right. That's going to be a line. That's going to be a parabola. That's going to be a cubic twist. You should know those things by the end of the year. Okay. Doesn't mean that you know exactly where it's going to land, but you should have a general shape of a general idea of the shape of it. Okay. What we're going to do today is we're going to clump all those things in what we call families of functions. So all lines are part of a linear family. All right. All parabolas are part of the quadratic family. And if we know that general shape, it allows us to graph a whole bunch of them very easily. Okay. All right. So families of functions. A set of functions in which each function is a transformation of one called the parent. So a family of function would be all of the functions that have the same parent. Your parent function is always going to be the simplest of that family. So our example here, we have linear functions. Y equals an x. Again, if you think of it as y equals mx plus b, this is our most basic one. It has a slope of 1 and it has a y-intercept of 0. Yes? Can you picture where it is on your graph? On a coordinate plane. Y equals x. Starts at the origin, right? Has a slope of 1. It's going to be a diagonal right through quadrants 1 and 3. That is our parent function for our linear family. All lines can be expressed as some kind of transformation of that. Okay? Same thing if I said our parent is y equals x squared. Okay? That is a parabola. Vertex at the origin, right? We can write all parabolas as some kind of transformation of that parent. And if we know what the parent function looks like, we can easily shift it to the new position for the new function. Okay? So we're going to spend 2 days talking about different kinds of transformations that we can do. The ones that we have available, we can do what's called a vertical or horizontal translation. A translation basically just means we're going to pick our graph up and we're going to move it somewhere else. Okay? A vertical translation means we're shifting it up and down. A horizontal translation means we're moving it left and right. Okay? We're also going to look at reflections and vertical stretches and compressions. There is such a thing as horizontal stretches and compressions that you'll learn about in your next math class. Okay? They're not included in this one. So let's start off with our translations. A translation, as I said, is just going to pick your graph up and shift it on the coordinate plane. Okay? It doesn't change the shape of it. It just picks it up and moves it. If we say that our parent function is just f of x, okay, we have some kind of function, and h and k are positive constants. Your function, the way it's written, is going to tell you if it moves up or down or left or right. If we have a plus k or a minus k on the outside of the function. So whatever that f of x is doing, there's something extra being tacked on at the end. That's a vertical move. It moves the way you think it should move. If I say I'm going to add something to it, I'm thinking I'm making it bigger, right? I'm moving it higher. It's going to move it up. If I'm subtracting that value, it's going to move it down. So your k is going to be a vertical kind of shift. If the constant is inside the function, so it's inside the parentheses with x, so that might look like x minus 2 squared, or the absolute value of x plus 5. Okay, it's inside whatever the function is, whether it's squaring, taking the absolute value, whatever. It's inside, then it's a left-right move. Okay? Our basic transformation format for all types of functions always has it being x minus h. The minus is built into it. Because of that, these moves are opposite of what you think they should be. If I see an x minus 2, I'm actually going right 2. If I see an x plus 5, I'm actually moving left 5. One way you can figure it out is think about what would make it 0. What would make this 0? A positive 2, right? So I'm going to move to 2. What makes this 0? A negative 5. So I have to move left to negative 5. Does that make sense? Okay. So in our pictures here, we started out with this function, f of x, and we shifted it up or down. For this function, it's a quadratic. We started with the red one, and we shifted it right and left. So the idea as we go through these today is we're going to graph the parent, the simple, easy one, and then we're just going to shift our points. Okay? So at no point in our stuff today will you be making a table of values for the complicated version. It's only going to be for the parent function. All right, so describe the transformation of the parent function, y equals x, so again, our basic linear function, to the new function y equals x minus 2. We start out identifying the type of transformation. Is this something we're adding, subtracting? Are we moving it up, down, or left, right? This one is moving down, right? The 2 is on the outside of x. There's no parentheses or anything clumping it with x. And it's a negative. So we should be moving down 2. So we're going to graph the parent function. To do that, we make a table for the parent function. Our parent function was y equals x. That means our x and y coordinates match. So I'm going to graph negative 2, negative 2, negative 1, negative 1, 0, 0, 1, 1, 2, 2. You don't always have to have 5 points. We just want it to be fairly accurate here. I typically write my parent function just with dots. If I am going to draw it in, I make it a dotted line or curve to show that that's my starting point. It's not my final answer. Okay? So the red dots represent my parent function. We said we want to move everything down 2. So picture taking your points and just shifting them all down 2. So this one moves down 2, down 2, down 2, down 2. I haven't changed the shape at all, right? It's still a line. It's just been shifted down. Now, I want you to think of this in terms of y equals mx plus b. What is the slope of that equation? 1, yes? My parent function had a slope of 1. That's why these two look parallel. What is the y-intercept for this one? -2. So instead of starting at the origin, I started at -2. That means I've shifted it down 2. Does that make sense? Okay. Our next one says, describe the transformation of the parent function y equals x squared to the new function y equals quantity x minus 3 squared. Let's start with this. What shape is it? That's our parabola. Let's get our graph for our parent function, y equals x squared. I want you to make sure to use some positives and some negatives in your table. What do we get if we take -2 and square it? A 4. -1 squared? 1. 0 squared? 0. 1 squared? 2 squared? You're going to have those points memorized. You're going to be able to graph a parent function parabola, y equals x squared, in your sleep by the time we finish here. All right, so I've plotted my 5 points. What type of transformation are we looking at here? Is this value an h or a k? Remember, it was y equals that type of thing, right? Is this an h or a k? It's an h. The stuff inside is our left-right, our horizontal shift. Okay, think h for horizontal. Which way is this shifting? Okay, so we want to take all of our points and translate them right 3. So let's take our dots. Each one of our dots is going to shift to the right 3. And then we're going to draw that in. So it is the same shape as the first one, the parent function. It's that U-shaped, but we've just moved it. Okay? All right. The first 2 examples we did had a single transformation. Now we're going to start combining them. And I will tell you right now, the order that you do these transformations matters. I could move things in a different order than you, and we'll get different graphs. So the rule is you do the transformations in order from left to right. Okay? As long as we have it in our basic transformation format, we can always go just left to right. So looking at this, what is the parent function? Y equals x cubed. It's a basic cubic graph. Okay? Do you guys know what a cubic graph looks like? Okay. So we know what parabolas and lines look like. A cube looks like this. Okay? We call it a cubic twist. Now, we can make cubic equations that are very complicated that can look like this. Okay? Have a really big twist to it. Or they can just be this basic twist at the origin. Okay? But that would be our parent function. Okay? A basic twist like that. What is it that we've done to it? What kind of transformations have we done? So work your way that way. What is the 1 going to do? It's going to go left 1. Good. So we've translated it left 1. What is the next thing we see? The -5 moves it down 5. Okay? Question 4 says, write an equation that will take the parent function y equals the absolute value of x. Do you know what an absolute value graph looks like? Anybody? If I said plug in a 0 for x, what do you get for y? A 0. If I said plug in a 1 for x, you get 1. If I said plug in a 2 for x, you get 2. If I said plug in a negative 1 for x, you still get 1. If I say plug in a negative 2, you get positive 2. So it is a v. Try to hit your dots there. Okay? Absolute value graphs are v's. Quadratics are parabolas, more of a U shape. Absolute values look like a v. Okay, so we want to take an absolute value function and we want to translate it. Notice I made the absolute value bars kind of far apart, right? Because we're going to put our h value in there. What do I have to put in my function if I want it to go 3 units left? A plus 3. And that has to be inside the function, in this case, the absolute value bars. Does that make sense? Then it says I want it to go up 2 units. So where does the plus 2 go? Good. All right. So that would take that V shape and it would shift all my points left 3 and up 2. Okay. Now, for all the functions, the parent functions that we've had, they've been ones that we recognize the shape of, or we could figure out the shape of. Here's one where they're just telling me the parent function is some f of x. I don't have an equation for it, but they've graphed it for me, and it looks like this black picture. Okay? So f of x is my initial graph. It says the graph shows the projected altitude of an airplane scheduled to depart an airport at noon. Projected altitude. Altitude is the same as height. So looking at our graph here, we have time for our x-axis. We have height in thousands of feet for our y-axis. Does this picture make sense if you think about a plane taking off? What happens when the plane first takes off? Goes up, yes? We hope anyway. Okay. Our plane takes off, it goes up. It's going to climb very quickly. Okay? So that's what we're seeing right here. Okay? It's going to go up very quickly. It leveled off for just a little bit of time. Then it climbed again. Then it leveled off for a little while. And then what happened? It starts descending. Yes? Your flight's over. It's going to get you back down to the ground. It's always a good thing when the plane returns you to the ground. Okay? What the question says is, if your plane leaves 2 hours late, what function could represent that? They've shown the picture in blue. They've taken the original black function and shifted it right to indicate that instead of starting at noon, we're going to start at 2 p.m. Right? Has the same flight plan, so it looks the same. How can I indicate with this function that I want to move it all to the right 2? I have to subtract 2. And I have to subtract 2 inside with the x. Right? Stuff inside is what's going to move it left and right. Okay? If I wanted to move this up 2, it would look like this. Right? The 2 would be on the outside of whatever the function is. Okay. Suppose the flight leaves 30 minutes early. Write a function to show that transformation. I'm going to pause this, give you a chance to talk to your table mates. All right. So what do we do with our function to make it leave a half an hour early? We want to add, right? Because we're going back in time to the left. How much? Y.5. Yes. X was in hours. We're only going 30 minutes ahead of schedule. Right? That's a half an hour. So X plus 1/2. All right. The last transformation that we're going to look at deals with reflections. I know in geometry you guys did reflections, yes? We are going to limit it to reflecting over one of the axes, the x-axis or the y-axis. Okay? So a reflection will flip your graph across a line such as the x-axis or y-axis. The original points and their reflected points are the same distance from the line of reflection. What we mean by that, if I have a point here, and let's say this is at 4, and I want to reflect it over the x-axis, it has to be 4 spaces below the x-axis. So it's going to be down here at -4. Does that make sense? Has to be the same distance. What happens if the point that I'm reflecting is on the line that I'm reflecting it over? It doesn't move, right? Because it's 0 units from the line, it's going to reflect and still be 0 units from the line. Okay. So we have 2 types of reflections. We can reflect over the y-axis, or we can reflect over the x-axis. Take a look at the pictures here. Our initial function is the one in black. If we reflect over y, we are taking a point like this, the point 1, 1, and I want to reflect it over the y-axis. It's going to land here at -1, 1. A point 3, 4 is going to reflect over the y-axis to be at -3, 4. Yes? Which coordinate changed? The x. Here the x was 3, here it's -3. Here it was 1, now it's -1. A 5 became a -5. When I reflect over the y-axis, it's my x value that's changing. X values change, y values don't. Okay? If my x value has to change, then instead of having just an x here, I'm going to have its opposite in the function. Okay? If I want to reflect over the x-axis, now I'm going to take a point like this, 5, 1, and I'm going to reflect it over the x-axis. It lands here. Now my x's didn't change, but my y values did. Okay? So again, it's opposite. If you're reflecting over x, it's the y value that flip-flops. So when I reflect over the x-axis, it's not the x that's changing, it's the y value that's changing. So instead of f of x, I'm going to have the opposite of f of x. Instead of my initial y, I'm going to have the opposite of y. So for reflections, to be able to tell which line you're reflecting over, you have to pay close attention to whether the negative sign is inside with x or outside in front of it. Okay. For this example, it says we're going to start with function f that says it is 3x plus 3. What shape is this? A line. What do we know about this line? Lines are straight. It has what kind of slope? Positive 3. And its y-intercept is 3. All right. So that's our slope. That's our y-intercept. So let's go ahead and graph it. We're going to start at 3 and do a slope of 3. All right, that's my original function. Now it says find a new equation, g of x, after an x-axis reflection. So we want to take all of these points and reflect them over the x-axis. Okay? This dot up here is at 9, so when I reflect it over the x-axis, it's at -9. This one's up at 6. Reflecting it puts me at -6. This one's at 3. Reflecting it puts me at -3. This one's at 0 for y, right? It's right on the x-axis, so when I reflect it, it's not going to move. And this one down here was at -3. I'm going to flip it up to +3. That is g of x. Try to hit your dots. Okay? If I asked you to tell me an equation for that line, what would you tell me? G of x equals, what do we know about its slope? Slope is -3, and its y-intercept is -3. I want you to be able to do that without graphing it. I want you to be able to tell me what that new equation is without having to put a graph on the paper. So we said that when we reflect it over the x-axis, we have to change our y values. So we are taking our g of x is going to be opposite what our initial y values were. Yes? So I want to do opposite the 3x plus 3, which turns into what we came up with, -3x minus 3. Does that make sense? So if I want to reflect over the x-axis, my whole equation changes sign. Okay? The last one here, we want to reflect over the y-axis, so which variable is going to change? Just the x. So h of x, this new one, is going to be the original function, but I'm going to change all my x values. Okay? So wherever there was an x, I'm going to substitute a -x. In my function, I had 3x plus 3. Now I'm going to have 3 times -x plus 3. Simplifying, we have h of x equals -3x plus 3. Now let's check to see if that's what happens. Take our initial red line again. We want to reflect it over the y-axis. So this point lands over here. This point lands here. This one doesn't change because it's already on the line I'm reflecting over. This point flips here, and this point flips here. Again, try to hit your dots. Does that match the equation we came up with? Is it a line that has a -3 slope and a +3 y-intercept? Right? Slope is -3, y-intercept is 3. Does that fit? Yes? Okay. So we will talk about the rest of our transformations tomorrow. I have one question for you, though. If I gave you that, what transformations have we done? And what's the parent? So let's start with the parent function. F of x equals what's the parent? What's the basic thing that's going to dictate the shape of this graph? That's squaring, right? The function is that I'm squaring something. It's a quadratic, okay? So if you want to think of it this way, my parent function is just y equals x squared, okay? I'm transforming a quadratic. We want to go from left to right. There's 3 transformations happening here. This is the first thing I see. This is the second thing I see. This is the third thing I see. So what is my first transformation? The very first thing I see is a negative sign in front of the x piece. Yes? Not inside with x, outside. So it's an x-axis reflection. Yes? Okay. Okay. What's the second transformation that I've done? Okay. So I'm going to translate left 3. And the third thing I see, I'm going to translate down 4. Does that make sense? So you always want to read it from left to right when it's in that basic format, because it will affect your graph if you do them in the different order. All right. So I will get you some graph paper. Here is your assignment.